today's keynote session. It's my pleasure to welcome you all, and we start immediately with the first point of our agenda, which is a presentation of the GOLC Award, the Global Online Laboratory Awards, and the awards will be presented by the president of GOLC, Valerie Varney. Valerie.
Thanks a lot, and good morning, everyone. Can I say good morning? Yes, it's 11 o'clock. It's fine. Okay. I'm sorry. Still in some time lapse. Yes, this is actually one of the favorite parts of the conference for me, and I think for a couple of us in the audience as well. Before I start announcing the GOLC Award winners, I would like to give you a little bit of insight for those who don't know what the GOLC Award is, or in which categories we give those awards out, and who is actually the person. Should I take this one? And who is actually the person to decide who gets a GOLC Award. So let me enlighten you on that. There is, as of this year, a huge committee, and we're very happy to have found a few new members. So some of them you might already know from the previous years, like Carsten Henke, I saw you up there, and Alexander Kist. Oh, you took off the hat. I wanted to say the man with the hat. So yes. So we've been doing this for a couple of years, and we're so happy that this year we found two new members in the committee. Anya Hussein, who is not here today, from the University of Washington. Maybe she's watching us, I'm not sure. If you do, hello. And Unai Hernandez-Yayo, where are you? Over there. So thank you very much. You've been a great addition to the committee, and I think we've seen some very amazing submissions this year as well. We have 3 categories, and I don't want to dive in too deep. If you want to know more, and if you want to maybe submit your laboratory in the next year, you might want to take a look at the website. There you can see we give out an award for remotely controlled experiments, and then for simulated and digitally visualized experiments. And as for a couple of years now, also the virtual and augmented reality experiments are awarded with a prize here as well. As we've seen so many very interesting things, laboratories in that area in the field for the last years. So let me introduce the first winner. For the remotely controlled experiments, I would like to ask Jakob Cekanski. I'm sorry, I practiced and then I did it wrong. Jakob Cekanski, please come forward. We would like to award you with the Remotely Controlled Experiments Award for your laboratory. So to do that, I would ask my assistant, Dominic, to come to the front with me. We'll be taking a picture. This award is for you, for your laboratory micro, the remote lab for embedded systems. Congratulations. So in order to take a picture, where should we go? Should we stand in front of this? Okay. So another round of applause. Very much. Again, okay. So, as the next award that we'll be giving out, it will be the award for simulated and digitally visualized experiments. And also here, we've seen some amazing contributions, and I would like to ask to the front Maria, Carlos, and Fiorella, who we've seen this morning already and yesterday. And thank you for your contribution. And congratulations to the award. Congratulations. So for the I would say final, but that's not true, for the third award category, virtual and augmented reality experiments. We had amazing submissions, and as we've seen in the previous years, sometimes we give out extra runner-up awards, and this is one of those categories where we do. But before I announce the runner-up award, I would like to ask to the front, Mesut, you're here, Altekin, thank you, Daniel Münstermann and Katrin Temmen. Congratulations on your award. Congratulations. Congratulations. And also, another round of applause for you. Thank you very much. So many people taking pictures. And as for the runner-up award, I would like to ask to the front, as we've seen a very interesting laboratory as well, with Spextra, the specialized process equipment training using extended reality, and I'd like to ask Majesh Chandramulina to the front. Congratulations on your runner-up award. Please come and join us here. Very much. Thank you. Yes. And for those who are asking themselves, okay, that's nice that you give out these awards, but we don't even know what they were for. There is the special session 1 after the lunch break today, which I highly recommend, in which the winners of the Golk Awards will present their laboratories for you to see. It's at 2:30 in the afternoon, and it's in room 213. So join us for this presentation, or for the presentations, and I'll see you after the break. And for now, I hand back to Michael to announce the keynote. So thank you again to all the winners, and see you later.
So now we come to the keynote speeches of this session. The first keynote speaker is Erwin Plett. Very welcome here. We met yesterday first time and had a nice talk during the welcome session. He's a chemical engineer with a global background. He studied at the university here in Chile. He studied in Karlsruhe in Germany. He studied also in the United States, University of Wisconsin-Madison. There's a long list of activities. I cannot tell you all this. You can read it partly on the conferences web and also in the internet if you make a Google search. Anyway, he has really a very, very active professional life, and some ideas of his thoughts he will now present us here. The floor is yours. Thank you very much.
So, good morning, everybody. I guess I have the ticket. Here we go. Can I have the presentation? Could you start, please? Okay, just went back here. First of all, I want to thank Duoc for the invitation here. Manuel Morales, thank you very much. And I have to tell you that I'm feeling home here. And you say, why the heck? Sure, I spent 6 years of my life here in this building. This was the former German school Deutsche Schule zu Santiago here, all this building. So I spent 6 years of my secondary in this building, and I haven't been back. So yesterday was the first time 50 years ago. So that's old. So now I'm telling you something about a startup. Academia Patagonia is a startup. We are two founders with the same age. We studied together. My partner is a mining engineer. I'm a chemical engineer. And after 50 years of experience, so among us, we have a century of experience in teaching, learning, and doing that. So we are down in Patagonia, which is at the end of the world, down on the left, South America, you know. Here we want to participate in this crazy stuff, which is an economy of hydrogen. And the question is very simple. How do I transport solar and wind energy overseas? How can I put the sun or the wind into a ship, which is difficult? How do you put the wind into a ship? It's not so easy. Okay, I have this in 4 sections. I want to tell why are we doing this, the international context. I want to speak about energy and emissions, which is something very important. I will tell you about Chile's potential for renewable energies. And here is a solution, how we transform electricity into other molecules. And that's called power to X, something you call electricity to something else, okay? Here we go. First of all, a small introduction in geography. Where are we? We are in this very strange long country that stretches on the left lower corner of America. Okay, South America, you see there, that is the size of Chile. We have 4,200 kilometers length. It's a ridiculous country. Okay, let's put just Germany. That is the true size of Germany. Okay, just as an idea, where are we here? I can put 4 countries. Look, I put Norway down here, Germany, France, and Spain, and this is still longer than that. So what happens? Look at that, that's Chile now if we project this to the northern hemisphere. So this country, here we go, look what happens. We do have all the rain and water in Norway. We have everything of, I don't know, biomass in the middle, and we have also sun from the desert. So this country is a very strange situation because we have all kind of weather in the extreme. This is just flipping up. Down in the south, we have a lot of rain and wind, and in the north, we have the driest desert all over. There are at least 300 days a year where you don't have clouds at night. That's why we have astronomical observation, and also at the day, there is no clouds. That means that the plant factor is very high because there is no shadow at all, okay? So that is where you're sitting now. And our startup is down here, and we are sitting in Santiago somewhere there. So it's about 3.5 hours flight to go down to the plant, okay? Here we go. So we are a startup, Academia Patagonia, and of course, since we are only 2 people, we have strategic partners. And I will just show you. The first one is Bildungswerkbau, Hessen and Thüringen. They are specialists in construction. You have to train thousands of people in construction. They have very good methods. The other one is very good. It's Smart Training. That's a Chilean startup, 14 years, and they have about, I don't know, they work in 7 countries. And they have all the technological side. Because why? We do have a problem in Chile. If you look at the adults and ask them to something, you will see 60% of adults cannot understand what they read. So you cannot send them a brochure. They say, Chief, what do you say here? Tell me. So it's a problem. And the newer generation even more. So what we do here is gamification. If people have their phones, you see with the 2 fingers, then you have to teach them with those methods what they are accustomed to use, and not putting into a front class with a paper because they won't understand. And then we have Burger. Burger is the largest here, have this tremendous crane in which we will build the aerogenerators. And they, for 40 years, have an academy to train people, because you cannot try to say, well, use this apparatus, cost about $5 million, and just run away. You have to be very sure they have no accident. So they have this training method. So we are partnering with them to see how we proceed now down there in Patagonia. Okay, international content. This is very important That is the energy consumption in the world, okay? We have an appetite for energy like crazy, and it's parallel to the amount of people living there. Up to now, you see, typical units. It's 633 exajoule. Exa is 10 to the 18. I don't want to have the zeros, okay? Or, as you have there, 12,000, what is that? Million tons oil equivalent. It's a little bit difficult, but okay, that's a way. So where would we get our primary energy from? Here, from oil, from coal, natural gas. Sure, 10% electricity, a little bit of wood, biomass. Everything else, we burn something to get our energy. All our society works on generating. I'm a little bit scared about ChatGDP and so on, because it will be a hell of electricity needed for that, really a lot. It's not a little bit. What happens now? Of course, we have emissions. Look, from 1750 to 2000, this is the way, just optically, look at the, well, you see, I like, as an engineer, talk about gigatons. Americans like billions. It's the same, huh? But you see, a billion in Germany is different than in the States, so prefer to use giga, which is 10 to the 9. This is what we have done as a humanity. And now we found out we have a problem. Houston, we have a problem. What do? We have to reduce. And by 2050, we want to be carbon neutral. And then we have a problem, because who is the guilty guy? Of course, the Chinese. You see, the Chinese, they have the most amount of emissions. Right. That's true, because by a lot of Chinese. Look at the United States, 14.4 tons per habitant per year. This is only 7. So now we have a political question. Who should pay? These guys, or should pay, I saw also, Indian guys. India has only 1.4 billion people, and they burn just dung. You see, it's a problem, because now who has to pay the bill of what we have done? So it's not fair to have Qatar with stadiums. They bought the World Cup, you see, stadium with air conditioning, 70,000 people air conditioning, absolutely crazy. Germany, 7.8, USA, 14.4, China, 7.1, Chile is a little bit above of the average world, 4.4, and India, 1.7, Africa, 0.7. How can you tell them they have to keep their oil underneath the earth? They have to develop themselves. So it's a political problem. I want to stress it out here, because it's not easy to handle this. Who has to pay the bill? So what we want to do, 2050 to 0. Do you think we will be able to do this? This is crazy. The appetite is more and more, and now it's a stop. We have to go to 0. This is something, wow, I don't know, politically, as an engineer, we can do it. The question is, can you sell that to the people? Okay, I will just now expand this one, which looks crazy, like something more sweet. Isn't that? But it's exactly the same, 2050. Crazy, I don't want to go, but just as an idea. We were talking about electromobility, okay? We said by 2030, 60% of the global car sales should be all electric, okay? Then by 2035, 50% of heavy trucks should be electric, and no more sales of internal combustion engines, okay? And by 2040, we have to be, here we go. It's blackout, no, here we go, yeah. 50% of fuels used in aviation should be low emissions or neutral. So this is, of course, and I shouldn't forget my hydrogen. We want to have by 2030, 150 million tons of hydrogen yearly. Today, we produce about 100, okay? And here, 435. But you see, it's a lot of things we have to do, not only one. There is no silver bullet. It's a lot of things that we have to do. Okay, hydrogen. Today, we produce about 9,500. And for what? For refineries, we have to desulfurize our crude oils. And then we do a little bit of ammonia, as you see here, for fertilizers. And the other one, just not to scare the chemistry, that is methanol, okay? Now, we want to, and that is what we use today. Okay, and here we go. I hope they are not refining any oil any longer by 2050. What else? We are changing completely now. We go into transport, and we will use, as you see there, methanol, ammonia, and this is dimethyl ether. Or in the industry. So we have a change completely. We don't need any hydrogen. It's enough. The problem is a gray hydrogen, and we want to have it clean. So we are using this as a vector. Nobody needs more ammonia, but we could use it for ship transportation, you see? So don't confuse the chemical use of this today with the energy use in further time. Okay, energy and emissions, of course. We have a plan in Chile. We have, of course, signed, as everybody else, more or less, the Paris Agreement, and we have this national distributed contribution, determined contributions, and we have a carbon neutrality plan. Chile is one of the only 27 countries in the world that had signed as a law to be carbon neutral. Everything else is promises, maybe we are thinking of, and so on, and we put it in a law. We saw this also yesterday. 75% of the emissions are due to the energy. A little bit of residues, a little bit of animals, but 75% is energy for electricity, for transport, for heating, and so on. So if we solve 75%, it's a lot. Then we can claim don't use any red meat and so on, you see. Argentina will have that problem because you have too many animals there, so it's a problem. But okay, that is where we're focusing. So what happened if we make a photo today in Chile? 64% of all our basket is fossil fuels, 98% imported. So this is a waste of money. It's not an investment, it's every year going out. Only 22% electricity, 14% wood, biomass. And we want to change that. And so we have different plans. Look at that. So decarbonizing, and that's a problem in Spanish, it's not only taking out the coal from the electricity grid, but also have the entire energy matrix decarbonized, so low CO2, and that's a problem. So what we want to do is from, say, 64, going up to 24 electricity, electrified to 42, 46%, depending on the aggressiveness of this plan. 36%, and we will never be able not to use any fossil fuels, but we reduce it to 35%. Here comes our hydrogen, and of course 5% wood. That is what we have as a plan to decarbonize, changing completely this energy basket. I don't like the name matrix. Nobody knows what a matrix is, besides a few engineers, but a basket is very clear. And I'm very happy because that in the law now is saying canasta is one of the things I have achieved, so very good. So we have a plan of carbon neutrality. Today we are emitting about 100 million tons. It's a small country, 100 million tons, and if you do anything, the business as usual, we will end up by 130. How the hell we get to zero? That's a challenge. We would be 130, so we have two measures. One is a biological measure. We capture CO2 in wood. What we have here, all over, this is CO2 captured, and you can keep it for 50 years, whatever, stored. That is CO2 which is stored. We don't have enough woods right now. We have to a little more, and then we come to a number of, I would call, technical solutions. First one, energy efficiency. That is the most important. Turn down the lights when you are not in the city and so on. Having parking lots 24 hours a day with light is ridiculous, okay? So energy efficiency, most efficient. Then we want to take out the coal firing from the electricity because we are based on coal. Use renewables, 11% electromobility. We'll have a contribution of 9%. And here where a champion green energy will be about 12% of the solution. 12% of the tons that we have to absorb, okay? So you see, we're not saying that we don't have fossil fuels, but we will absorb, and that is a way to get to carbon neutrality, zero. So we absorb the same that we emit. There are only 5 countries in the world that today are carbon negative, have more woods than they are firing coal, okay? Chile's potential for renewables, here we go. And I guess better I show you a short video.
Climate change is the greatest challenge we have ever faced as a species. The urgency of global warming forces us to shift our perspective, to look for new answers. Chile, with its unparalleled natural wealth, is set to become one of the main players in this mission. with the planet's best solar radiation and the strongest southern winds. It can potentially contribute to carbon neutrality worldwide by generating green hydrogen. The potential market for green hydrogen is estimated at $2.5 trillion US hydrogen and its derivatives, and become the most competitive producer of green hydrogen worldwide. We are the first Latin American economy to join the OECD. Stable policies that promote investments. Free trade agreements with 90% of the world's GDP. We are the world's leading copper and lithium producer. The potential installation capacity of more than 70 times the current electrical capacity. And we're just getting started. Together, we invest and build a clean future now.
So that is the potential. And now I want to do a little bit arithmetic with you, because we are talking about energy. The German GIZ and the Corfa have done a map of Chile, in what region we have what kind of renewables. You see, we're talking about photovoltaic, CSP, wind, and so on. Every single region has its potential. And if you look at that, solar photovoltaic is about 1,200 gigawatt, okay? Solar CSP 550, and so on, marine, hydropower, whatever. That's what we have. And now the problem is you do not have to sum up this, because this is pears and apples. You never sum potential. What you can sum is energy. Why? Because, and here I will tell you the first formula. I know that every time you write a formula, you lose 25% of the audience. So only one, only one there. Energy is power multiplied by times, okay? That's all I want to show, not more than that, because I want to do. So what is a plant factor? It's just a percentage of the yearly hours at nominal capacity. So if I have a photovoltaic field and I pay for 1 megawatt, I want to know how many hours I get a megawatt. And that is completely different of the geography. In Europe, you can put it in Spain, the best solar, you will have 20% of a plant factor. The same photovoltaic field, all the way to Chile, Atacama Desert, you will have 37, with same investment. But it's different where you put. The same happens with wind. The best wind you have is in the North Atlantic, on the sea. So this is offshore. And we do have better situation in Patagonia onshore. So that is the difference. So this costs 1. And if I put it here, it will give me 50% of the hours in the year, the 1 megawatt, and then you have 75. So I will produce a lot more energy with the same investment. That is the difference. So you have just an idea. Coal fire will have a plant factor of 80%. You have to do maintenance once in a while. Nuclear has 95. Every, I don't know, 4 years, you have to change your uranium. So it has a very high plant factor. And we know that at night we don't have sun. So we have a problem there. Okay, now that I know plant factors, I can get, again, the formula the same. It is what I said, but now I can put a plant factor to that. So what happens? 1,260 gigawatt is exactly the same energy that 550 in solar concentration. Wow. So you never have to add it, but you can do, this is petawatt hours. Peta is 10 to the 15. It's a lot of zeros back here. And exa is 10 to 18. So 18 zeros acá, which is ridiculous. So I have exactly the same. 3.9 petawatt hours is exactly the same. Then 14 exajoules. And now what can I do? I can sum up. This is what energy I can at the end of the year, okay, this year. What can I do with that? 9.6 petawatt hours a year. Okay, hydrogen has 33.3 kilowatt hours per kilo. Let's say that electrolyzers have 70% of commercial efficiency. So I can produce 200 million tons of hydrogen per year. That is double what today the world needs, okay? What else? If I compare the 34.6 exajoules a year compared with what the humanity swallows today, we have 5.5% of green energy of what the world would like. So this small country, if I compare it with how much electricity we produce, this is kind of electricity a year, we have 150 Chiles. So we can save, I don't know, 5, 10 for growing, everything else we could export. So that is a good news that here we do have a lot. Okay, so the potential is what I told you there, 144. So what happens? This small country only produces 0.25% of emissions. So why do you care? We are so little. I know we are not part of the problem, but we could be part of the solution. As I say, we have 23% of copper reserves, 51% lithium reserve. The difference, this is proved reserves. The availability or the source can be, the biggest source of lithium is the sea, but it's so diluted that you cannot use it a commercial site, you see? And what happens, our lithium is very easy to get from salty waters in the north. 5.5 per minute. So we could play a role being part of the solution. So we could generate twice the gray hydrogen produced today or 6 times the gray ammonia. Crazy. But look, the National Green Strategy only will use 50% of this potential up to 2050. The next generation could use the rest because we need a lot of money for this. It's not so easy. Okay, power to X. So electricity. Okay, we know they have renewable electricity, but here we have a problem. We have what I call dispatchable electricity and non-dispatchable. Dispatchable is when the consumption needs that, I can deliver that, okay? Geothermal, hydro storage, biomass, I can burn biomass whenever I want, but I don't have solar at night. It's a problem. Wind, I don't have every time wind. So here are non-dispatchables here in a row. Look at that. This yellow peak is at midday, so this yellow is solar electricity. Perfect, okay, but only in the midday. Then I have the green here is wind. For 2 days, I had little wind on the whole country, and then I had more wind. Perfect. What can I do? I can have hydro. I can, when the wind goes down, I can open a valve, and I have more hydroelectricity. Perfect. Everything else, I have to burn something. That is in black up there. To have the, you see the demand is changing. At night, nobody wants it. We have a peak on the afternoon when everybody is going home. Turn on the TV, I don't know, cook something. We have a peak. It's not an industrial country, so we have a peak in the afternoon, and that's a problem. So this non-conventional renewable energy is highly variable. And then we have a demand which is variable. So we have an engineering problem here. So how we compensate that? With storage. And look at this. Normally in electricity, you always speak about generation, transmission, distribution. Yesterday we had a talk about distribution, the grid, okay? But we forgot all the time that we always had storage. We always had storage of potential energy, of chemical energy, and then we can, now we have this problem, we have to change these two, 1 by 2, because I have to generate when there is sun or when there's wind, and then I have to store. And I can tell you, store electrons is the most slippery stuff you can have. It's very difficult to store electrons, okay? Then you can transmit and distribute. But this makes a problem, okay? What kind of technology we have? Okay, you know, I can store electrons. These are capacitors. It's the one, you have the starters for the fluorescent light, the neon light, it's small. It gives you a spark, and then you have electrons. But now you have supercapacitor. Okay, that's it, but it's for very short time. Then you can store the electricity in a mechanical way, like pump hydro, compressed air, liquid compressed air, inertial spinning. Okay, that's a way of storing electricity. Thermal, okay. Sensible heat, like we do in these big towers. We have molten salts where we store our energy by 550 degrees C, and then we have a conventional thermal electricity, but without chimney. That's the only thing. Thermochemically, and then batteries. Everybody knows lead-acid batteries in the car. what we are storing there are ions. I have to move the ion from the cathode to the anode and then back again. So it's not electricity. You have to. But I cannot put a battery into a ship. It will sink. It's too heavy. The density is not good. Okay, so what we do worldwide, 91% of the surplus electricity is stored in pumped hydro solution. How you do? You have a small lake or a river down and have one up. When you have too much electricity, you pump it up, and at night or at the weekend, you get it down to the turbine and make electricity again. This is very good. Norway does a lot of this. Germany, you have to. It's an efficiency of 75%, so it's not too bad, what you can get back. But you can store tremendous amount of megawatt hours. Okay, 5% in battery electric storage system. And I always say this is electrochemical way of storing electricity. And then we have a little bit of heat, perfect 3%. And now we invented our completely crazy, using hydrogen, this green hydrogen. Of course, you have liquid hydrogen, it has a lot of energy. Remember that the NASA sent guys to the moon using hydrogen and oxygen. You burn that too and you go to the moon, as simple as that. It's the most energy per kilogram, and that is what you need to fly to space, okay? And yes, there is one ship going around between Italy and Australia and Japan, okay? So, but we know hydrogen is a problem, but then we come all the chemistry. I don't need to store hydrogen. I could put methane, I could put ammonia, methanol, dimethyl ether, and so on. So we can go to the chemistry to be able to put a lot of energy into a ship to go overseas. Here we have our renewable fuels. We always had renewable fuel. We had biomass to go to the moon. NASA didn't care about cost. You had to win to the Russians, so it doesn't matter what it costs. Now it's a problem. So we are not using that. It was one of the most users was at NASA in the United States, but minus 252. That's 20 Kelvin. See, it's cold. Huh? So there is one. So the liquefying temperature, yes, you have where we have a problem. Hydrogen minus 252. Yes, there is this one ship going on between Japan and Australia to see. I fill it up with liquid, how much I get when I go to Japan. Nothing, a little bit, boil off how much I do. What can we do? We can go to methane, minus 162. And this is how worldwide we transport methane, natural gas. In Germany, it was in record time, they built 2 terminals for that. With permits, everything was crazy last year. Chile had also a problem. We got our methane from Argentina. And from one day to another, Argentina said, no, no export. And we had built all our pipelines, everything. We digged all the streets, and we had no gas. So in a very hurry, we had to build also 2 terminals. The first one costed $1.5 billion, the other one too, so costly stuff. But we had this energy event in Chile because of we couldn't believe at our dear brothers in Argentina. It was a political problem, not technical. Okay, propane. This is the bottles of liquid gas. You see what we are traveling around. It minus 40 degrees, so it's transported all over the world in a ship with minus 40 degrees. We have a technology for minus 40 all over. If you have ambient temperature, you will have 7 or 8 bars. So you have this bottle, it's heavy, but you can work all over with LPG at room temperature with 8 bars, okay? Then we have ammonia. Ammonia is liquid at minus 23, so if I have this technology, why not? In the moment in the world, they are transported 20 million tons a year ammonia. Chile is importing ammonia. It's too little, the amount we have here, 350 kilotons. 13 ships a year that come with ammonia at minus 33, we store it at minus 33, and use it for explosives and for fertilizers. Dimethyl ether is very nice because it's 2 times, yeah, here we go. It's 2 methanol minus 1 water. It's this horse, the small one. But this is an exchange to diesel, 1-to-1. I can use in all diesel machines that, and has even a better cetane value as diesel. So I don't have no change, nothing on the truck, I can use dimethyl ether. And then we have our methanol, okay? This is burning alcohol you have all over the home. You see, it boils at 65 degrees, so you have it at home. Don't drink it, please. This is a problem. Don't drink it. We like ethanol, not methanol, okay? People have problems with that, okay? So that's a way. So if I have methanol, I can put it in a ship and and transport it worldwide. Wow, this is a project of hydrogen in Chile. The north is on the left. Don't memorize that, please. 75. I just want to show you what happens here in the southern part of Chile, okay? What happens? I want to ship the wind, power to X for the wind. So I have a lot of wind there. But then I have a logistic problem. I cannot ship wind. I cannot ship electricity from down there to Japan or so on. So I have to have other molecules to be able to ship that. Then we have this tremendous project called Highly Innovative Fuels, which is sponsored by Porsche. Yeah, the German government gave to the poor guys of Siemens 8 million euros to produce this, 8 millions. Not 350, 8 million, okay? So there is also German money in that. And they produce methanol and also e-fuels, okay? The only one. And everybody else is using ammonia. Why? Because ammonia, you get it for free from the air. And the problem in methanol is this black spot, the carbon. Carbon has to be, for that, has to be also green or bio. So you have, either you have direct air capture, what they're doing right now, or you get it from biofactories. So it's difficult to get this carbon with the idea that is biogenic. Okay, you see, so logistics said you have to do ammonia, nothing else. So how you do? Here you have the HIF plant. This small blue line is the Magellan Strait. So on this side is the continent and the Feuerland is on the other side. Okay, here we go. I will show you what we have. We have wind, a lot of wind there, okay? And with this wind, we produce electrons. You see the small e? Yeah, that's electron. What do we do? And then, again, we have water, H2O, okay, in this green stuff. And then from that, we split the water in hydrogen and oxygen. The same that plants, maybe it's 50 kilograms, but you can put on the normal pressure into that. So it's very difficult to move hydrogen in a gas way. So what do we do there? The trick is, in this get a truck in this case, with CO2 coming from Argentina, from a brewery. The CO2 from the brewery, of course, is biogenic. So in this very moment, there are trucks coming with the CO2, and then you just stick the hydrogen with the CO2 in the very big factory down there to produce methanol and e-fuels. This is gasoline 95 octanes. That is something magic. So at the end of the day, we have wind, and we end up with a liquid, which is either methanol or gasoline. Of course, we have these visible advances. In Chile, we have a plant here in Quilicura, which fill up about 250 forklifts with hydrogen. They took out the heavy batteries, electric one, and put now the fuel. So they're very happy because instead of waiting 10 hours for charging the battery, the filling of hydrogen is 3 minutes. So it's a win-win situation. It's very expensive. It's only 0.7 megawatts. But for 240 forklift, it works perfectly well. This is Walmart, okay? And then our president, which comes from that, is here again. We are exporting. This is the first one. You see 25,000 liters in one ISO container. There is the energy of the wind going to the world. This is, they use Porsche for car racing, clean car racing. You have 100,000 people with gasoline, but the guys racing have this clean gasoline. But it's marketing is very good. So now we go. What do we need for developing this hydrogen economy? Very easy. You need technology. You need financial capital. You need governments, legislation, regulation, which is not that easy. And here we go. We need human capital. And in this Congress, we're talking about this part, human capital. How much? 2021, the GAZ made a history, and if we only comply with our natural contributions, we need 94,000 people in this industry by 2050. They haven't been born yet, okay? But we need 94,000 in this country, and we start to export. Okay, what institutions are there? Okay, university. Yes, I'm a professor in 5 universities, okay? We are here at the DUOC, which is a technical formation center, you see, tertiary. We have the schools, technical professional schools, up to the 12 degrees, but you can get out full of guys. Technical professionals, quite a lot. And industry, crazy. And we are working on this side. It costs gigadollars or billions. We have one Energy, which is a Danish consortium. It will need 5,000 people, and the investment is 11.5 billions. This month, there will be another project going, one project in the north. INA is about 11 billions, and the biggest one is coming in from Total Eren this month, is about 15 billions. So huge project, which took 4 years or so to have the basic engineering, on-site studies, where are the squirrels, where are the birds, and whatever you have to. If that is okay, by 26, 27, we could have the final investment decision. And then we start investing to put all those billions into the sand, in the desert, wherever. So I guess the project execution will be about 5, 6 years. So the first drops of ammonia, whatever, will come out by 2030. That's the reality. So people are getting nervous, calling me, when are these projects, when are they ready? It's not so easy to spend billions. It takes some time. So we don't need the people right now. We have some time to train them. That is the good news. We have time enough, because you don't need operators of hydrogen if you haven't built the plants. So we have time enough to prepare ourselves, prepare the training to do this. Okay, my conclusions now is Chile has a tremendous potential of renewable energy, as I told you, 150 times the current electric energy production. The challenge, and that is my talk, the challenge is how to transport this clean solar energy overseas. How I come to Japan, to Korea, whatever, which is not so easy. Our national green hydrogen strategy that was published in 2020 wants to have a business of 33 billion annually by 2050. And that is the order of magnitude of mining. You see, we sell other things like fish, salmon, it's 7. Fruits, also 7, 8. So this is the biggest business we have thought of. So it's a tremendous opportunity of this country. We have a green action plan with 81 specific actions with accountability. So it's not only, so here, who does it? This is a public-private coordination with accountability, and that is good. You have an action plan. Who has to do what, when? And of course, human capital formation is the key strategic element for reach this unique opportunity. Everything else we can import, also the money, but the people, we have to create them here. So that is our tremendous opportunity we have. So thanks for the attention. I'm open to questions.
Thank you so much. I think we could ask you.
Please, and we have to, it's now, every time, you see, here in this one, I saw they are buying the CO2, okay, because you can get it from a brewery. Right now, MAN, which is from Volkswagen Group, is installing a direct air capture. How you get back this 400 ppm into a bottle? You need pins, one molecule here, one the other. So you have to use a lot of energy to capture this CO2, and that is, it's expensive. And that is the only part of the technology which has not been proved worldwide. That's why they are building a tremendous tower in a batch system. First, you have to get rid of the water in the air, so it's just silica gel, and then you use alumina to get the CO2, and then you have to evaporate it again. So that is an expensive and technology, non-proof technology to make gasoline. No problem, that's a Fischer-Tropsch, done for 100 years, so it's not a problem. But the technology of direct air capture is...
You say the number of people who are qualified in this field or for this field is so tremendous high. And we know Chile, 20 million, for example?
18, no?
18, okay.
With a very low natality rate, it's a problem.
Okay. Can Chile solve this challenge by their own citizens? Or is there a promotion initiative from the government also necessary to convince these people to be trained in this field? Otherwise?
You see, I said at the beginning, we need so many people by 2050. I guess they haven't been born yet, when they are 30. So I'm asking for help, please. Give me the guys we need. We don't have them. You're right. It's a challenge, and you're competing with electromobility, whatever, but this is a unique chance. I don't know, maybe we import people, which we did for the photovoltaic at the beginning, which was crazy. We got guys of Bulgaria, whatever, to build up our photovoltaic field. Now we know how to do it. And this is a completely new thing that everywhere we're trying to see, what do we need? How do we make ammonia or so on? We have to train things that this chemical industry doesn't exist in Chile. So we're starting from scratch. And that's a tremendous opportunity. You're right, it's a challenge where to get the people from. It's a lot of automation. And don't be confused. The most part of this is construction, civil construction. It's a little bit, the operators are all automated. So you need in a room 2, 3, 4 guys, maybe maintenance, but the big jobs are in construction. The project I told you is from Total Eren, which is coming up, it has 7,000 kilometers of internal routes. You have to go, it's crazy. But you have to have a road from one windmill to the next one. So there is a lot of construction to be done. So in all these figures, it's not only the operators of hydrogen, it's all the construction industry. We have to build ports. We have no ports there. You have to put this into a ship. So we have to have a lot of infrastructure. That is in this number. For having this industry, you need the Goni. I have to do it in the middle of winter with a lot of snow, which is not easy. You see in mining, you have to fly the guys and then after 2 weeks, get them back. So you have to have hotels. They don't have anything. And one example, I like it, and you can provide me with 10,000 fresh eggs a day. This is just an example of, it's not hydrogen, eggs. Somebody has to clean 5,000 bed sheets a day. Who does it? With the concern, environmental concern that the developers want. The one project, you cannot have, you have to see all the things you need. I don't know the cases for that. You have to see how you recycle them. So it's a lot to do. It's a new industry. It's not only the chemical side, the construction side is even bigger, yeah, on that. There is, please.
Thank you very much. It's not on, right? Is it? Okay. Thank you very much. That was very inspiring. And what I loved here is to sell this topic as an opportunity instead of like something to like work on as a society and like develop backwards. I love that a lot. I, if you allow me, would ask a broader question. So coming from Germany, voices are getting bigger and bigger and more prevalent of people saying, do we really need to become neutral by 2050? Is that even necessary? Or asking questions like, well, we are not the big part of the problem here. Our country is too small. And actually, what you just said, that Chile is not part of the problem, but maybe part of the solution, sparked my question. And I was wondering about what is the discussion here in society and in politics around that goal. Is this like broadly supported, or is it in question? Is it like questioned more and more? What is kind of like the feel of it at the moment here in the country?
Very important question, because we are simple engineers and we are scared of politics and all these, the guys, we don't like politics, but we are not influencing and we have to. Look what happens here. In Chile, the only ministry that has a long-term planning is energy. We have a plan, Energy 2050. None other ministry, not in health, not in education, we change educational plans every other year, which is crazy. It's not a politics. In energy, we had in the 2 governments ago, we had this plan 2050. Even every 5 years, you have to make a modernizing of that, and we have done 2. Then the energy policy was done by the last government, a right-wing government. I was named their energy ambassador, whatever, and now this government completely left, see? They say, oh, this opportunity, we can't miss that. So this government did a tremendous public coordination. There were 11 ministries sitting, discussing what we need, infrastructure, whatever, health, and so on, 11 ministries talking about that, what we need. And from there comes this action plan, which is very good, that also this government, this is not a government problem, it's a state problem. And that gives us continuity, because otherwise it's crazy, you see? What happened in education is absolutely crazy. But here in energy, we have a long-term planning, because if you ask a guy to put a few billions, he said, and what tomorrow? Huh? We don't like Trump saying today this, the other one. Nobody will invest if this is uncertainty. So I do think we need certainty in taxes, which is something. I have to be able to make a calculation. I cannot say this is an investment like, I don't know, making an hotel. You build an hotel and after 2 years you are gone and you don't care. But this, your money is stuck for 20 and 25 years. So you have to have certainty that your investment, that they'll give you your money back after 25 years, because Copenhagen Investment Partner is an investment firm from pension funds. You don't need the money now, but you need the money in 25 years. So you have to be sure to get the money after 25 years, and you're earning some money here. So this long-term planning is very important to have the credibility, and luckily enough, Chile has this. We are not a country jumping out. That's why the investment in mining are also 20 and 30 years. And then you need certainty. Otherwise, I will not bet my money. So that is the question. Will you bet your savings in this? I don't know. You have to convince politically the people that this is a tremendous opportunity we do have here, but we have to give security to the investors. And that is a political problem that I cannot inaugurate anything. That's a problem. Politicians like to cut the line and make an inauguration, so short term. And here for that we need long term, and it's a problem for a developing country to do long term stuff. So excellent question, and yes, we are confident that with this action plan 2023, 2030, we know what to do in 1 decade, and that's good. It's long term. That we have to do a lot of things, yes, politically a lot too. Because you see, up to now, hydrogen was a dangerous substance regulated by the health ministry. And then we had to change the law saying, look, hydrogen is an energetic. Oh, now the energy ministry can take care of that. Up to now, energy ministry had nothing to do with hydrogen. Up to 2 years ago, energy ministry had nothing to do with wood. Everybody is buying wood, and they were just looking around because it's political problem to have all the small farmers cutting wood and selling green wood. So they didn't want to touch, so you could look. Okay, but that's the situation. Thank you. Anybody else? There is a question up there, please.
You presented a very compelling. You're presenting a very compelling narrative. Like, you know, I'm really excited about it. What I'm struggling, or what we're all struggling, I think we don't see that kind of discussion in the public discourse as much. You know, there's, as Dominic said, you know, in Germany, there's people questioning climate change and so on. In Australia, I think a lot what you said would apply in Australian context as well. You know, we have a lot of wind, we have a lot of solar. That would be a very compelling narrative to change the industry, the focus of industries in Australia. But it's definitely not part of the public discourse in Australia at the moment. I wonder, is it part of the public discourse here in Chile? And what could we do, you know, to, like you said, you're an engineer, we are engineers, true, but I think even to a non-engineer, you're presenting a very compelling story. So, you know, how can we take that out in the world, into the world?
Yes, it's not easy, because you said today what you're doing is unfair. I'm burning oil, coal, having these emissions, and then running away. Somebody else will have to get rid of the CO2. That is not fair. So at the moment where you're not doing putting a CO2 tax, for instance, is a problem, because you see, we talked about this yesterday, you have to get right signals. And I guess from all our senses, like humans, the most important or sensitive sense, do you know what it is? Your pocket. So if you not convince people to have taxes, it's crazy. You see, a very nice model. Do we have the Swiss? The Swiss guys have a CO2 tax of about $100, okay, the ton of CO2. The nice thing is that it's not a tax, it's a redistribution. So everybody will pay the CO2 tax, and at the end of the year, you divide the amount of money by 9 million Swiss, and you get everybody back. So the one guy who drove to the work in a car has contributed, and the guy driving a bicycle got money back. And that changed the behavior. So again, we are not saying the truth if we have subsidized fuels. And it's a problem, because you always subsidize fuels because poor people, they have no money for fuel and so on. At the level of the whole world, this difference in prices, which is a subsidy, is about $500 billion a year. What is a substitute is the difference between the international price and the national price. As simple as that. How much you could get if you, I don't know, you sell your gas in Rotterdam or you use it here. So poor people, you see, I'm working with a guy in Bolivia. The cost of gas in Bolivia is $1.2 a million BTU, 1.2. And the same you could get $50 in Rotterdam. So they're wasting their gas to produce cheap electricity because poor people. If we would have had all these subsidies put on renewables, we had another, because in 10 years we have $5 trillion. So it's tremendous the amount that we are really subsidizing, and it's a political issue. I had a fight with our minister. The same, we are subsidizing electricity. And I don't know, they think that they have to subsidize electricity. They say, why don't you give them money? The lights on all day is because it's too cheap at the end of the day. So that is a reality. Thank you for your questions.
Thank you so much for this really inspiring talk and discussion, and I'm really sorry to have to break this now. But I think it's very important thoughts for all disciplines of engineering. Engineering is one of the bases of engineering, and so it's very important for us all. Now we come to a second problem. You already told us that education is a very important thing for all this. I have the pleasure to introduce now as the second keynote speaker Uri Kuckerman from Argentina, from UTN Argentina. He is there the director of the Center of Education. He has also international positions in some universities as a visiting professor. And just yesterday, he told me that he was elected a week before or so as member of the Argentinian Academy of Science, of Engineering Science. Congratulations, and we are keen to hear now your thoughts about engineering education.
Good morning, everybody. While I prepare my computer, please, you prepare your phones, because I will ask you to use your phones in order to interact in Okay. Again, good morning, everybody. Buenos días. Guten Morgen, is this correct? Thank you very much, Manuel, for inviting me here. I really like this country. I've come in so many different occasions for vacations and also for conferences. So it's a very nice place to visit. We need to change our mindset, and I asked myself if we engineering professors, faculty, we are able to change in the national, sponsored by the National Academy of Engineering, which, as Michael has just told you, appointed me as a member. We developed there a research project in which we research about how the university professors all over the world are really prepared for teaching engineering. But before showing the results of that research, I will ask you to answer 3 questions. Now, yes, please use your phones, your notebooks, or whatever you have there connected to the internet. And do you consider yourself prepared to teach engineering? I have received 1 vote so far, please. I don't know if this is working. No. No. Oh, yes. Now I will show you the results. So you are answering that yes, you consider yourself prepared to teach engineering, 61%, I'm not sure, 22, and no, 16. This is a fairly good result. Let's go to the second question. What does it mean? What does it mean to be prepared to teach engineering? Please answer that question. Sorry? I don't remember. No, I guess you can select several, yes. Okay, we have fairly good number of answers. So let's see. 28% have practical experience in engineering. 27% be able to teach complex concepts. And 26% be familiar with teaching methods and other skills. 19%. So this is showing us that we engineering professors, we need very different skills in order to teach engineering. And as I will show you in the following presentation, not all the engineering professors in different countries in the world are really prepared for teaching engineering because they don't have all these skills. Let's go to the last question. Is having an engineering degree let's see. Well, there is a problem here. Let's see. Oh, here. Okay. I need to show the answers. No. Okay. I've done this in several different places, and I always receive the same kind of answer. 80% say that having an engineering degree is not enough to effectively teach engineering. But as I will show you in a few minutes, most of our professors only have an engineering degree, or the only requirement is to have an engineering degree in order to teach. And there we have, again, Houston, we have a problem. And this presentation will go further into this aspect. So I will finish this, and let's continue with my presentation. This is the research I mentioned to you. We got more than 1,000 answers from 45 different countries in 6 continents, so it's a very wide survey. And these are the results. What is the discipline of your undergraduate degree? 82%, not for surprise, are engineers or other professions related to technology. Only 10% have an education degree, and 8% other kind of degrees. Then the second question, what kind of training have you received? And you can see here that 38%, the green zone, have not received any teacher training. 27% voluntary courses offered by the institution where you work. So this might be a 1 week course, a 1 day course, I don't know, a few hours, something like that. Former career related to pedagogy, 25%. So you can see that most of our engineering professors are not prepared for teaching, because teaching is not something that you can do, I don't know, improvising. You can do engineering improvising. You can do medicine improvising. You can do law. You need a 4, 5, 6 year study to be a lawyer, to be an accountant, to be an engineer. But to be a professor, you don't need any training. I'm an engineer. I've been teaching for more than 40 years, but I discovered some years ago that I needed some kind of training, some kind of education in order to teach better. That's the reason why I got a PhD in education, because I felt myself that I was not doing a good job just by teaching engineering without a pedagogical training. And that's my point in this presentation. To what extent do you think that educational teacher training should be a requirement for university teaching? You can see it should be offered and encouraged, but not required, 44%. Why not required? It should be offered and then demanded, 32%. It should always be required. So the professors all over the world think that it should be in some way a requirement, but not for me, for the others. 34%, it has contributed a lot to quality of learning. So they are saying that by learning how to teach, they are better professors. And well, another 34% has contributed relatively to the quality of learning. And I can share with you this research. It will be published in the National Academy of Engineering soon, I guess probably next week or so. It is in Spanish. We will try to translate it to English in order to be available for all the people. Now I want to speak a little bit about the demand for engineers. Our colleague here, your name, sorry, was Erwin. Erwin was speaking about the demand for engineers. And we have not only figures from Chile, but from all over the world. USA needs 400,000 new engineers each year. The gap between new engineers role created and new engineers entering in the US market each year is stark, with about a third of new roles unfilled. I will not read everything. You can read it by yourself. But the same situation happens all over the world. You can see here in Germany a shortage of 320,000 STEM specialists by 2022. India needs 1 million engineers specializing in high-tech areas. In China, the shortage is of 5.5 million engineers by this year. So we can see that this is a very serious problem. And some fact, well, also about the world in general. 75% of employers report having difficulty filling positions, especially in technology-related fields. And also, the demand is not only for related with quantity, but related with quality. You can see here the top 5. We've done this for centuries. But are we really prepared to teach these skills? I mean, to teach, not to ask the student to do this by themselves. We ask them to work in teams, but are we able to teach them how to work in teams? We ask them to communicate well, but are we teaching them how to communicate well? All these kind of things, we need to include them. These kind of things we need to include in our curriculum. We need to include in our programs. And we as professors need to be able to teach those things. We are facing a set of unprecedented challenges. First, democratization of higher education, which is good. Of course, we need to cope with this demand. We need a lot more students in the engineering schools. And democratizations mean that we have more and more students. I don't know how the figures are here in Chile, but in Argentina, the number of university students is rising. That is the good part of the story, but the bad part of the story is that we are not prepared for training, for teaching those new students. The updating of labor demand. Again, the demand, the industry is asking for engineers that are prepared in a different way, not in the same way as I was prepared 50 years ago, or 45. Automatization and artificial intelligence, both are very important skills, very important challenges, that are facing our engineers, and we need to prepare our students in order to work with automatization and with artificial intelligence. The most common discussion in our universities, how will I know that my students are preparing their homework, their essays without artificial intelligence? I think we are missing the point. We need to train them to use artificial intelligence in a better way. Not only trying to see if they are cheating us or not. That's not a problem. Digital transformation, and by saying digital transformation, I'm not meaning that we will use more notebooks, more cell phones, and more internet. No, how can we transform our institutions, I mean the universities, in order to take advantage of all these tools to improve the kind of education we are offering? For example, using artificial intelligence in order to personalize education. Are we doing that? I don't think we are doing that. Accreditation. Well, we are all under the ABET rules and the national rules for accreditation, which is good because this kind of accreditation processes improve the quality of our institutions and the quality of our programs, etc. But then again, it's a challenge because it requires a lot of preparation, a lot of training, and finally, the consequences of the pandemic. The pandemic is over, thanks God, but the consequences are still there because we change a lot of things. We are using Zoom, we are using the virtual campuses, we are offering courses online, much more than we did before the pandemic, and this is here to stay. This is not something that went away when the pandemic was over. So we have to deal with all these challenges, and in order to deal with all these challenges, I think that is important, that is really necessary to train our professors in order to be able to deal with all these challenges. So, some ideas I want to share with you about how I think we can cope with these challenges. First, develop and implement collaborative interdisciplinary strategies. Usually, I don't know in other professions or in other schools, when we speak about the university, I don't know how much interdisciplinary work they are doing. For example, in my university, we are working with engineers, not with other professions. And I think we need to do that because the actual problems in the field are solved by interdisciplinary teams. So our students need to learn how to work in interdisciplinary teams. Promote educative innovation. Together with my colleague here, Juan Palmieri, we have a Center for Educational Innovation in our university, and I think each and every university need to have, each and every engineering school need to have an innovation and educative innovation center in order to promote innovation, which it is not necessarily related with technology. Technology is only one way of doing innovation. Innovation in a more broad sense means innovation related with methodology, new methodologies, not only new technologies. Advanced, well, the same, advanced innovation in education. Educating the educators, that's what I was speaking about. Professors need to be trained in order to be good teachers. Otherwise, we will fail as teachers. Enhance teaching methods, which is in the same direction, and ensure inclusion and equal access for all. And this is not necessarily or not only bringing to the university, to the engineering school, people from underserved communities, but be able to level the different yes, the different opportunities they have had in life. What? So we should include in our curriculums and be prepared to teach what? Creative thinking, critical thinking, ethics, social and environmental implication of engineering, teamwork, communication. I ask you now, by raising your hands, for those who are professors in engineering schools, in your curriculums, do you have these points in your, yes? Who else? Some, very few, more or less. Well, we need to include these aspects in our curriculums. And also, we need to train our professors in order to be able to teach these things. It's not easy to teach creative thinking or to teach critical thinking or even ethics. It's very difficult. It's not that easy. It's not just saying, you need to be an ethical person. Okay, that's not enough. You need to think creatively. You need to think critical. What does it mean? How can we do that? We need to be trained in order to train to educate our students to be able to have these skills included in their preparation. Well, I have already asked you this. So just to end my presentation and to open the discussion, because I think the most important part of a presentation is the discussion, the conversation among colleagues. This quote from Albert Einstein, most teachers waste their time by asking questions that are intended to discover what a pupil does not know, whereas the true art of questioning is to discover what the pupil does know or is capable of knowing. Another very interesting anecdote, in one of these conferences some years ago, a CEO of a very important international company was invited to speak, to have a presentation like this one. And one question was, how do you select your new employees? And that man said, without any doubt, those who are able to pose the best questions. And I said, oh, this is wonderful, because we are teaching, we are preparing our students to answer questions, not to pose very good questions. And we have to have this in mind. And then my question is, what kind of questions are you asking? Because the quality of the questions are probably the most important thing, more than the quality of the answers. The answers are there. When you look for them, you will find the answers. But nowadays, with artificial intelligence, the most important part of using artificial intelligence in a good way is how you prepare the prompt. What is the prompt? The question. If you prepare your question in a good way, you will receive probably a good answer. But if you pose a bad question, you will receive a bad answer. Well, that's all for my part. Thank you very much, and I'm open to more than questions, to discussions. I want to discuss this with all of you. Thank you very much.
Uriel, thank you very much for your inspiring talk. I was thinking while you were speaking, you asked the question, do you have that in your curriculum? Yes, we do. I'm from TH Cologne, and during the pandemic, I came there in 2020, and they had reformed their master's in mechanical engineering. And it has all these things.
Great.
But what happens now is we're in the reaccreditation process for the curriculum. And what happens is my respected colleagues, I think they fear that these things that we teach them, these competencies that we try to enhance, take over, and the students don't know enough in mechanical engineering anymore. So I was thinking, what would you tell them if they were your colleagues? What would you say to them? Because what I see is a group of students that are very good in reflecting on what they're doing and critically thinking about that. But what the colleagues see is they don't know the same as we did when we studied engineering.
Thank you. And this is the very first question that appears in every place I go, and I say this, so thank you for bringing this up. You know, what I used to say is that they are looking through the back mirror, not through the front. They are thinking in this way: if I was trained in that way and I'm a good engineer, why this is not useful for my students? And what I answer them, this is not useful for your students because your students are not like how you were when you were a student, and the society is completely different. So you need a different approach. That's the first part of the answer. The second part of the answer is that we professors, we prepare our course syllabus using the book index. And we put in the syllabus all the subject that the author in a different country, in a different situation, probably was asked by the publisher to put a lot of chapters because that means more pages and more money for the publisher. So you have a very long syllabus with a lot of subjects, and some of those subjects will be useful in 5 years, and some of the subjects that the students need to know haven't been invented yet. So my suggestion for those professors is to focus in the conceptual things, those things that won't change, and try to keep them as short as possible. We need to change our mindset in order to realize that it is not our obligation to teach everything. They will need to keep on learning through their whole life. So the most important skill they need to acquire during the 4 or 5 years time is learn to learn. And we need to develop that skill into with our students. I don't know if this answers your question. Yes, please.
I'll drop the microphone up here, if you don't mind. Sorry, I jumped the queue.
Okay.
Your presentation, excellent. It's really speaking from my heart as well. Like I'm feeling very strongly about this, and we in fact went through the process of implementing a modern curriculum that addresses and has a lot of those things inbuilt and more, to be honest. One of the things we observed, all the things you're talking about, that our staff don't necessarily have the skills in education. But another question I wanted to pose to you, and having a lot of pushback at the moment from staff along the lines of what Valerie said. But my question is really even pushing it a bit further, because what we observed is that a lot of our staff who have originally an engineering degree, they're not really engineers. So what I mean by that is they're in those positions because they're doing research, and while they're doing in general engineering research, if you look what they're doing, they're really scientists. If we ask them to explain engineering, really what an engineer does in the workplace, a lot of them don't know because they never worked in the industry. They did their PhD, were a postdoc, they know how to publish papers without end, but they don't really know engineering. So we are at the point where it's at least half of our staff, while they said they're engineering professors, that don't know what engineering is, and they don't know how to educate students. So that's a real problem, I think.
Yes, you're right. And in another part of that research, we asked them about their engineering practice, real practice. And we discovered that there are very different situations in different countries. For example, in my own university, we have a lot of, may I say, real engineers or engineers working in the field that come to the university to teach. But then the problem is that they are not interested in spending time in learning how to teach. They come and and on the other hand, you have those engineers that are scientists, researchers that haven't been exposed to industry, and they know a lot. They have a lot of knowledge about the fundamentals, but they haven't seen, you know, what happens in the real world. So I think the solution might be a mix, to have some professors that have more engineering experience, real engineering experience, and some other professors that are more related with research and with the scientific part of the story. It's not easy. I don't have the perfect recipe for solving this situation, but we need to be very creative in trying to find the best way. Certainly, the old way of teaching, I mean, by saying the old way of teaching is having engineers without any pedagogical training. Teaching is not the best solution. It's a very how can I say, very challenging subject, and we need to try to find good ways to solve it. It's not only related with engineering. In medicine, it happens exactly the same. Yes.
Uriel, thank you very much for your excellent presentation. And I just can see from my point of view, I had no teaching at all in teaching, but I'm teaching for 50 years. Starting in the university. So I learned by doing, and I have good grades, and I have no idea. And see, in our startup, I learned completely new things that I cannot have a super teacher, superman, superwoman. I have to work with other people. So right now we have academic investigators, we have guys teaching pedagogy, we have instructional designers. I didn't know that. Something completely new. I had no idea. We have audiovisual equipment. We have 3D modelers. We have front and back end programmers. Not teachers, you see. We have experts in user experience.
Yes.
What the hell is that? Okay, you see, I'm an engineer. We have a development of video games for teaching. And I don't pretend that an engineer will do all these others. So we have to integrate these completely different skills, but not in one person. There's no way that I will be, I don't know, a designer or instructional designer being a teacher, other guys. So at the end of the day, you have to work with a lot of other people teaching that. And just one thing of the question we had in Karlsruhe, you cannot be a professor if you have not been 3 years in industry. So it's no way that you publish papers, you have to solve real problems. Otherwise, you will never get a teacher degree or a professor degree. So it's another way. You have to come from the practical side to be able to teach. You have learned with the industry to solve problems, otherwise you don't get your money. As simple as that. You cannot get, and this is a different, I thought about this project we are doing. As an engineer, it's crazy. I'm doing something now and I have the result in 10 years. By teaching is marvelous. I can see immediately if my students are sleeping or they are paying attention. So I have an immediate reward. You see, so I can calibrate if I'm getting out my message because I can look on the eyes, which is a problem now with Zoom. You see, but you can see it. So you can feel if you are contributing with something or the guys are sleeping. So it's a very short term. So I doubt that they can have a super teacher, a superwoman with all the things you have done. How do we proceed? We have to work with other guys who know something else.
Definitively, definitively. That's what we were doing from probably 20 years ago. When we began our research related with education, we developed a team with engineers, pedagogical experts, and psychologists. And by working together, we learn from each other. And we kept on doing that permanently. And for example, just to tell you a very short example, but related to what you are saying, just 2 years ago, I prepared a paper, first a research project and then a paper, and we presented that paper in a conference in Colombia, a pedagogical way using the user experience techniques. And we presented that. It's published in a Springer book, so you can find the results of that. I think that's the best way to solve this situation, to work collaboratively. We are asking our students to work collaboratively, to work in the interdisciplinary teams, but we are not doing so. And that's part of the solution of the problem. I'm not speaking, I'm not trying to convert each and every engineering professor into a PhD in education. This is my own crazy way of doing things. But this is not what we need to require our professor. I find it very important to ask our professor to have industry 1 week each and every year, every 2 years. I think it's enough to keep them aware of what is happening out there, what the research related with education is, which kind of new methodologies are out there, which kind of new technologies, how to apply those new technologies in a best way, because it's not just to put the computers in each and every desk and think that this will solve the problem. That increase the problem, not that doesn't solve the problem. I guess we have we don't have more time, so thank you very much.
Thank you very much for the discipline of the speaker. I think we had really a lively and interesting a session with many questions, but also many answers. My thank goes to the two speakers here, and I wish you a good lunch break. Thank you very much.